Hello everybody, it's a big pleasure to be talking at this international workshop. My name is Maksym Radziwill. I am a mathematician. I'm currently at Quran. This is basically the NYU math department. My main area of interest is number theory, and this is where most of my work is. But I'm also interested in probability and dynamical systems. So as you can guess, I'm on the analytic side of things. And you might wonder, okay, why am I talking at this international workshop? Well, I've been actually interested for a long time in low-level aspects of computer science, and that includes both hardware and software. And it's an interest that I haven't really published much on. This is basically a hobby. And regarding Plan 9 in particular, I have an interest in it going way back to when I was a teenager in 2003. And you can actually find some of my posts from that time on this mailing group, Comp.os Plan 9. And back then I used to be specifically interested in distributed operating systems, but eventually I moved on and I did other things. So around last year, I actually rediscovered that Plan 9 is still being developed under the name of 9front. So of course I was tremendously excited, and I immediately installed it on my computer, read the man pages, catched up on the things that I forgot. And the basic question that I have, and I think anybody has, is can I use this as my daily driver? And I decided to use this operating system as the one that I'm using in my office, as an experiment to basically see how usable it is. And the more I use this operating system, the more I like it. But as everybody, I stumbled into one of the first bottlenecks is that there's no actual browser in Plan 9 that is usable by modern standards. So of course we have something called Motra, and in many ways it is very nice. But given the state of the modern web, it's not particularly usable. I mean, besides being slow, we immediately run into problems with JavaScript. And then, so this is really, the browser is the main issue, and there's another competitive browser called NetSurf, but it still wasn't quite enough for me. And the other two problems for a mathematician using Plan 9 is that there's no big LaTeX distribution. There is a slimmed down distribution, I think, called KTeX. And this is not quite enough because we actually have certain expectations as to fonts and packages, and KTeX didn't quite cut it for me. And then the other big one is, of course, also the PDF viewer, which on 9front comes out to something like this. And this is actually quite decent, but the issues are more when you zoom in, it is not so pretty. Okay, so these are kind of the main issues to usability of 9front as a daily driver, at least for me. And so there are two immediate solutions to this problem. I mean, the first solution that everybody advertises is don't port these programs. They are impossible to port. I mean, web browsers are millions of lines of code. So instead, just try to run these programs on Linux and embed Linux inside your workflow on Plan 9. So the two solutions that are commonly suggested is to either use VMX, which is a virtual machine to emulate Linux, or to use VNC, which is basically connecting to a Linux desktop and seeing it on your 9front desktop directly. So let me discuss both of them. So VMX is a really beautiful virtual machine. It's beautifully designed around reading and writing to two files. So it basically gives you a text interface to capture each time that a virtual machine exits, does I/O, or interrupts. And you can also control the virtual machine re-entry through the CTL file. But there is a downside to this, is that each time that you're reading, well, you have to make a bunch of syscalls, and you also need to parse text, both in the kernel and the user space. So overall, there's actually quite a bit of context switches going on for each virtual machine operation. So overall, VMX is not maybe the fastest virtual machine. It's actually quite fast for how nice the design is and for how few lines of code it has, but it's definitely not the fastest virtual machine out there. So when I tried to run Firefox on VMX, it wasn't quite really working as nice as I would like to. So I tried naively, this was my first attempt, I tried naively to add SMP to VMX. I said certainly that will make it faster and then have a usable Firefox. And so this actually helps, but not that much. And just to show you how it actually works, let me show it here. So here you see, here is VMX, and I added SMP support. So you can see the 4 cores in here, in the H-top. You see them being displayed here. And now if we are going to start something like Firefox, so unfortunately, okay, you see the core starts spinning, okay, boom, we have Firefox, and if we go to Wikipedia, you see it's almost full load. It's not fantastically fast. Let me put it this way. And then we can finally click, but you see the CPU usage is quite high, and then finally once it's loaded, then actually we have a smooth experience. Okay, so this is for VMX. Okay, so this actually, so adding SMP was definitely very interesting for me personally, but it was not did not actually solve my problem. And another kind of bottleneck with VMX is that there is no GPU support, and browsers actually use GPUs quite a lot for rendering these days. So that's another source of slowness. And at the end of the day, I did not benchmark this, so I don't know what is the actual main issue here. And it also could be that all of these issues basically compound. Okay, so now let's get to VNC. So with VNC, the issue is a little bit different. So VNC actually transmits an entire frame each time at each update. So it actually transmits the entire screen. So what happens is that VNC is actually quite slow on like a 10 megabyte per second network, like the one I used, which was basically Wi-Fi. But as I just discovered before preparing this talk, it actually becomes quite usable on a 100 megabyte per second network, because its network usage is basically around 80 megabytes per second. So let me also illustrate how this works in practice. So I will start the VNC server, and then we are going to connect. Okay, and then so let's see what can we do with this. Okay, so immediately it's confusing because you have 2 window managers, and this is confusing for the user. And one other minor issue of VNC is that, okay, here it maximized correctly, so this is actually quite usable, but you see if you shrink the window, it's a bit weird. It's being cut off. It's being cut off in a weird way. So this is one unpleasant aspect of using it. The second one is that you actually have 2 window managers at once that you have to deal with, so 2 window management styles. And finally, the other issue is that you are using a lot of network bandwidth. You see, like, for example, just for typing some words, well, okay, it's not so bad here, but okay, 50 megabyte per second once I'm scrolling, for example. And even opening a pop-up creates 30 megabyte per second. Okay, so this is for VNC. Okay, and there are actually kind of common drawbacks of both solutions. So in both cases, you end up running a window manager inside the window manager, so that's confusing for the user. And the second issue, which also affects both, is this issue of resizing the window. So in VMX, it's basically not possible. Once you have decided on certain dimensions, that's it. You have to just have this dimension. And in VNC, I mean, also there's a maximum size which corresponds to your screen, and that's it. If you're going to make it a bit smaller, then it doesn't actually adjust. And both are actually resource intensive. So VMX is CPU bound, and quite a bit so, and VNC is network bound, so it actually uses a lot of network bandwidth. And finally, there's another small issue that I didn't appreciate until I ran a 9-front terminal. So if you want to run VMX on a 9-front terminal, you actually better attach a hard drive, a physical hard drive to the terminal, so that you can actually load the disk images from it. Because if you're going to be loading the disk images from your remote file server, it's going to take quite a while. And finally, both solutions actually involved quite a significant amount of code on 9-front. I mean, VMX is an entire computer emulator, and for VNC in particular, we need to implement the VNC protocol. And that's a bit antithetical to the design of 9-front. We would like to have actually everything using just 9p. In the sense the 9p protocol should be enough for everything. And so there is an alternative to these two, which is VL9 due to Michael Forneys. And his idea is, I think, really beautiful. His idea is to just export the dev draw device over the network, and then we are going to write a Linux 9p client, which will connect to our host, and just directly display on the draw device. And so specifically what the Linux client is going to do is going to output the output of the Wayland clients directly on the draw device. And so one of the benefits of this is that Linux applications are going to run as if they were native on 9-front. In a sense, you shouldn't be able to tell them apart. And there's also one remaining issue. I mean, if you want to share the file system, you will have to do some extra plumbing so that you can also access the 9-front files on Linux if you want to do it. But you can. I mean, there are many ways of doing this. But unfortunately, there's a problem with WL9. And the problem is that it implements a really minimal set of Wayland protocols. So, for example, as far as I understand, it doesn't actually implement pop-ups. And Wayland is a quite big, complex, and expensive protocol. So the upshot of this is that I couldn't actually make WL9 work. So I know that some people managed to make it work, and those people managed to run Chrome, but they couldn't run Firefox. And then most other applications also didn't run. And finally, also, this is again what I heard, but I cannot confirm, that user input was slow in WL9. So what is actually p9wl? It's basically just a continuation of this idea. It's a Wayland compositor, and instead of doing something from scratch, it's actually based on wlroots, which is a library for building Wayland compositors due to Drew default. And the idea is the same as WL9. We export the dev draw device on 9-front. Then p9wl is a headless Wayland compositor. It connects to the dev draw device. Then any Wayland app connects to p9wl, and p9wl draws the output on the draw device. Of course, the draw device is not the only one that is being used here. We also should accept keyboard inputs, so we should also connect to the keyboard device. We should accept mouse inputs, so we should connect to the mouse device. We should also handle copy-paste, so the snarf device. And finally, the window control WCTO device. So let me actually demonstrate how this works in practice to give you a taste of how this program is used. So there are two versions of this program. There's the one that is currently on GitHub, where the top level is permanently maximized. And in this setup, if you start a new app from a terminal emulator, you don't have a new window which is being forked. I think this is actually preferable, because it has a similar feel to the current 9-front graphical applications. And then there is a local variant, which I have still not posted, where basically you fork a new Rio window each time that you execute a new Linux program. So this is actually closer to what WL9 intended to do. But the downside is that you actually need the RC script on 9 front, which actually handles the window management part of it. And there's also a few other additional features which differentiate p9wl from WL9. So first of all, there is broad support for Wayland features. This is thanks to it being based on wlroots. But there's also a lot of bandwidth optimizations because, as I mentioned, I was actually running on a network which could at most cut 10 megabytes per second. So I was quite sensitive to using as little bandwidth as possible. So in particular, one thing which is possible thanks to using the DevDraw device, we can actually easily add compression, and even more interestingly, we can add scroll detection, so similarly to what video codecs do. And there is also one more feature, so there is TLS support, but this is just a convenience. I mean, you could actually do the same thing by wrapping everything into S-tunnel on Linux, and then TLS serve on 9 front. Okay, so now let me demonstrate how this actually works, and then I'll come back to the slides again. So let me illustrate these ideas by running them on a 9 front host. So I'm going to start 2 windows, and in one window I'm going to export the dev folder on port 10,000. And in the second window, I'm going to run an application on my Linux laptop. And the Linux application is going to be, of course, p9wl. And I'll pass to p9wl the IP address of our 9 front host, which is this one. And I'll indicate that we are exporting the dev device on port 10,000, as you can see here. And then the next argument is Firefox. So what this will accomplish is that it will start a headless Wayland compositor on Linux. And this headless Wayland compositor is going to execute Firefox and pass its Unix socket address to Firefox in an environment variable. So then the output is going to be displayed on the DevDraw device, and the headless compositor has access to the DevDraw device because it connects to port 10,000 where it's actually made available. So let's see what happens. When I run this, I actually see Firefox. So indeed, I can now use this as if it was a standard Linux application, because it is. It's actually running on Linux, and it just displays on 9 front. And all the usual Wayland feature works, so zooming in, zooming out, the pop-ups, which are always a little bit tricky, and moreover we can even copy paste. So if you take copy, and then here you can, sorry. So okay, here I'm going to copy, and now I can paste. Okay, sorry for this. And in the other way around, I can take some text here, and I can copy it here, and then I can paste it here. So this is working just fine. And eventually, okay, you're going to maybe get tired of running Firefox, though there is one more thing that I want to show with Firefox. So there is a lot of compression going on in this program, so much that you can actually even play videos when you're working on a LAN. So I'm going to make the screen a little bit smaller to make the video higher quality. And as you can see, you can just watch a video. Of course, when you watch a video, the bandwidth is shooting up as expected. And so what would happen if instead of running Firefox, we ran a terminal emulator? So let me start a terminal emulator. I'm going to send it. There we go. We have a terminal emulator. And now the big question is, what will happen if I start Firefox? Well, what will happen is that this is a Wayland compositor, and the way it's implemented, it always maximizes the top level. So if I start Firefox, I'm just going to have it overtake the entire screen, and if I exit, I'm back to the terminal. So this is done on purpose because it emulates the kind of behavior that you see in Plan 9. If you open a terminal and you start a graphical application, it just overtakes the entire window. Alright, and you can also, for example, open events if you like, and zoom in, and this. Okay. Alright, and okay, eventually of course it's going to get a bit tiresome to start two windows to get access to Linux application. So you can package all of this in a convenient script. And I have actually two sets of scripts. I have one script for one local Linux computer and another script for my laptop, which I don't always have with me. And if you notice, here the fonts are bigger. The reason why the fonts are bigger is that this script is invoking my program with this following argument, which is minus s1.5, which means fractional scaling by a factor of 1.5. So when you have fractional scaling, some features actually disappear. One of them is certain optimizations related to scrolling. This is not something that you will notice on a LAN. I mean, on a LAN, scrolling is just completely fine. In fact, even if I maximize, it's completely fine. But you will notice this if latency is around 50 milliseconds, then you will actually notice the lack of this optimization. And finally, one more thing. So if you don't like this way of window management, I have been working on an alternative program, and this program actually starts a genuine new window each time that you open a new graphical application. So for example, if I type Firefox, I actually get a new window, and you see if I type events, I get another new window, and so on and so forth. And eventually, of course, you're getting completely swamped with new windows. So your system starts to look like Linux rather than 9-front. Also, finally, one thing that I find convenient is I package these scripts into Rio so that I have access to them straight from Rio. In this way, I can open a 9-front terminal, a Linux terminal, and my Linux terminal on the laptop with the same mouse movement. So I found it actually quite convenient in practice. Okay, so we are back now from the demonstration. This video was actually done in 3 cuts, and actually I just noticed after the first cut that there was this black screen over this. I'm sorry for this, I don't think it really makes much difference. The only thing that you missed is that you didn't see the bandwidth spiking up to 30 megabyte in this box here. Okay, so let me now discuss the actual implementation of p9wl, or at least the parts of it that I consider most interesting. So the basic idea, as I already said a few times, is that on 9-front we export several devices, notably the draw, keyboard, mouse, WCTO and snarf devices. And then p9wl connects to these and starts as a headless Wayland compositor. And then it executes a Wayland app and provides its Unix socket in an environment variable to it, so that the Wayland app communicates with a p9wl thinking that it's a standard headless Wayland compositor. And then p9wl uses a wlroots hook, and the hooks are callback to be called once anything new is displayed. And once anything new is displayed, it actually sends it to 9-front. As a result, it actually maintains 2 frame buffers. It has one frame buffer which corresponds to what is currently being displayed on the Linux host. Let's call it Linux FB. And then it has another frame buffer which corresponds to what it thinks is currently displayed on the 9-front frame buffer. And let's call this one plain 9FB. And of course there is a bit of a lag between the two. I mean, the Linux one has the immediate correct information, and the plain 9 is always a little bit delayed compared to the Linux one. And so one of the biggest challenge in this program is to actually keep the two as synchronized as possible. And in order to keep them as synchronized as possible, we obviously want to minimize the delays in the transmission between the two. And this means in particular that if we want to minimize the delays, we aim to transmit as little data as possible, among other things. And so there is this whole question of how do we minimize the amount of data that is being transmitted by the program. And the first mechanism at our disposal is to use Wayland damage tracking. So this is a feature of Wayland basically Wayland apps can advertise to the compositor which parts of the image have changed, so that the compositor doesn't need to look through the entire screen for new changes. And this is actually a good faith effort, so there are no actual obligations to report this correctly or accurately, and many Wayland apps actually just say that the entire screen changed, even if just a little bit changed, so there are no obligations. But it's still a good optimization to use, and in fact this is the only bandwidth optimization that Michael Forneys implementation uses. We are going to use a few more compared to that. Okay, so we use this as a first approximation to narrow down to the region that has actually changed. And then what p9wl does is that it splits the screen into 16 by 16 tiles. So of course your entire screen is not your entire window is rarely a multiple of 16. So what we do is that we have an internal frame buffer which is of 16 of 16, but we actually display just a little chunk of it. I mean, not the entire thing, we display a chunk of it, but the whole thing internally in memory is 16 times 16 aligned. Okay, so now that we have the Wayland damage region, we actually check each tile within this region for changes. And then we transmit only the tiles that changed within the damage region. So this is the second optimization. And this is really, this actually really kills a lot of bandwidth. I mean, it really gives a huge gain. And then, since we're actually transmitting to the draw device on the in front, the draw device actually has a lot of capabilities. Among one of these capabilities is the ability to decompress the images that are being transmitted to it. So, since we communicate with this device, why not use its capabilities fully? So in particular, what we do is that we can actually compress the tiles using LZ77 and transmit those compressed tiles to the draw device and tell it to uncompress them and display them. And then, so this actually works well for, for example, new images. But if you're going to see animations, it's actually a bit wasteful, right? Because if only one pixel has changed, it's obviously wasteful to retransmit an entire tile that could have many colors. So this is a next optimization that we can do, a third optimization. I was one off in my listing. So what we can do is that we can also look at the pixels that change, and we can transmit only the pixels that actually change with a opaque mask, so that they overwrite what is written before. And we compress simply those pixels that we want to overlay, okay? And then what we do is that we can check whether this, whether compressing just these new pixels is less than compressing the entire tile. And if that's the case, we compress the only the changed pixels. Okay. And so, I mean, the draw device can accept both. It can accept compressed items, and it can also accept this bit masked tiles. Okay, and then there's the fourth optimization, which to me was actually the most interesting one. So I spent, in a sense, the most time on this, but I would say it's, in some sense, it is an over-optimization, but it's actually quite useful over slow networks. And so what this optimization is that we can actually, when you scroll in a browser, it's very wasteful to transmit an entire new image, right? If you scroll just a little bit, you're actually not, you have gained just a little bit of new information, just this little range that you have scrolled. This is the only thing which is new. But if you only use what we have discussed so far, you're actually forced to retransmit an entire new image, because when you scroll, the entire window actually changes, even though the amount of new information that you receive is actually just this thing at the bottom. So it's obviously very wasteful, something very wasteful is going on, because you end up retransmitting the entire window, even though you're learning only a little narrow band at the bottom when you're scrolling. So what we would like to do is that we would like to actually detect when a scroll is happening, And then when a scroll is happening, we actually would like to send just a short command to the draw device saying that you should scroll the current screen on line front, and then we should send the new bits that come in the region that is actually new. So this would be the optimal way of handling this. And so what I end up doing in this program is a little bit more flexible. I actually do two things at once. So I actually always do scroll detection, and then the algorithm always detects a scroll, but it could be spurious. And then after the scroll is detected, it shifts the frame buffer and computes how much has changed and how much new compressed data should be transmitted. And then we also do a second thing. We actually don't do scroll detection. We just check how much has changed and how much should be transmitted once compressed. And then we decide which one to do based on which one actually takes less data to transmit. So this actually alleviates me from having to decide what constitutes a sufficient scroll or a sufficiently reliable detection of a scroll. Okay, so now how does this scroll detection actually work? So we split the screen into a number of regions. Each region is of size 256 by 256, and we detect scrolls on each of these regions separately. So this actually makes sense because if you, for example, use something like events or a browser, you notice that when you scroll, it's not the entire screen that is scrolling. Usually there are things like the pop-up which don't change, or in events there's a bar here that doesn't change and just the text inside changes. So it makes sense to actually split the screen into these smaller regions and then just detect scrolls within each of them. So how can we detect a scroll? So the most simple and naive algorithm would be to just take this region, sample. So you have the frame buffer from before, you have the new frame buffer, and you want to detect if there was a scroll in between the two. So the simplest thing that you could do is actually just pick up a bunch of points at random and see if these points differ by a fixed amount. So you have to actually sample the scroll amounts too. So it's not a really, it's a really naive algorithm. You have to actually check all the possible scrolls and then pick a number of points at random and check if they differ. It's kind of wasteful, and also if there's just one pixel that actually changed and you get unlucky, you don't detect the scroll. It's not great. Okay, so what would be maybe a smarter way of doing this? So this is the way that actually suggests itself right away to a mathematician. Well, if you have a translation, you should always take the Fourier transform. This is how we think. I mean, if something is translated, take the Fourier transform, see it on the Fourier transform side. So let me explain the mathematical setup and then how the Fourier transform comes in. So imagine that you have a blank screen, and on the screen you have an image, and let's call this frame buffer 1. And now imagine that you have the same frame buffer, but the image has been translated by XY. And let's call this frame buffer 2. And then how to describe a frame buffer? Well, we can just decompose every color into 3 components, the RGB components. And so we have 3 functions, one for each component, R, G, and B. And each of these functions describes the intensity of R, of G, and B at the point UV. Okay? And then you can think of these functions however you want. I mean, you can think of the UV as pixels, in which case, U and V, it's like in which case it would be like a piecewise function or rectangle. It doesn't matter how you think about it. Okay, so let me denote F1R, F1G, F1B, these RGB functions for the first frame buffer, and let me denote by F2R, F2G, F2B, these RGB functions for the second frame buffer. Okay. And so if we really have a shift, then for each of these RGB colors, these 2 functions are actually related by a shift. Okay? So what we want to detect is we want to detect this type of relationship between 2 functions. And moreover, we want to be able to detect this type of relationship even if this function is a little bit disturbed by some noise. That's actually the main point of what we do. We want to say that even if you add some random noise to this function, you still should be able to detect this relationship. Okay. But for the moment, let's just assume that we want to detect this type of relationship between two functions. Okay. So how would you do it? I mean, the standard way for a mathematician is to take the Fourier transform. So what does the Fourier transform does? It takes our RGB function and it decomposes into waves. So what this function does is that it actually tells you what is the amplitude of the wave component of this function, where the wave is described by this complex exponential here. Okay? So if you haven't seen Fourier transforms before, this is quite a lot, I agree. But I'll have a little picture later, so it will be more clear what this actually does. So it might make more sense later. But this is kind of a actually easy thing to see. So this is just the definition of the Fourier transform. It's just you take the original function, you multiply it by this complex phase. You see, so C is coupled to U, eta is coupled to V. You integrate over U and V, and this is a function of C and nu. Okay? And then, since this function f2c is related to f1c in this way, you can make a change of variable, and you see that f2c is related to the Fourier transform of f1c just by a multiplication by a complex phase. So in particular, what this means is that if the two functions just differ by a translation, then this product of the first Fourier transform times the second Fourier transform bar normalized by their magnitudes is actually just a complex phase. So how would you so what you need to do is that you need to detect this ratio being close to a complex phase. You see, this is the idea. The idea is that if you can detect that this ratio is close to a complex phase, then it means that these two functions are basically translates of each other, even up to some noise. So how do you detect whether this is a complex phase? Well, you can apply the inverse Fourier transform to this function. So you take this function and you multiply it by basically the same thing, but just with the minus sign. And let's call this function fuv, okay? And then what happens is that if it's really true that this function is close to a complex phase, then this function is going to have a gigantic spike at exactly coordinates x, y. And so once you detect where that biggest spike is, that gives you a candidate for the actual translation that happened. Okay? And why is this an efficient algorithm? It's efficient because you can actually compute Fourier transforms quickly. I mean, basically in average time big O of 1 for each entry that you're computing. So this is the idea of the algorithm. Okay. So what is the actual advantage? So if you had something which is so exact, I mean, this algorithm looks a bit like I'm doing something overcomplicated, right? What's the point of doing something so complicated for if there is an exact relation? The point is that this complicated algorithm actually works well even if the function f2c is only approximately a translate of the first function, in the sense that even if you add some noise to f2c, this algorithm still actually detects the translation correctly. So let me actually, this algorithm is a basic instance of what apparently video codecs do, because they apparently try to detect your motion and then use this, since they can, they can compress better if they know where the rough motion is going. Okay, essentially they construct a vector field of the motions. Okay, so let me illustrate this with a picture. I think a picture will make it easier to understand. So here you have an image, you see, and here I'm going to take its Fourier transform. So this is, I'm drawing the level sets of this Fourier transform. And you see that the biggest level set is actually at 0 here, basically at 0. This is where it takes its biggest value. So this is actually one interesting feature of images. They usually have a spike in the Fourier transform. And now, now here's So by the way, if this image was just random noise, right, then this would also be completely random, right? So the fact that there is this spike is actually meaningful. If this was a completely random signal, you would also get a completely random signal here, and this algorithm wouldn't actually work so well. So this algorithm actually is using the empirical fact that for most images, the Fourier transform has basically a spike, a well-defined spike of its level set. Okay, and so now let's take a black rectangle. So if you take the Fourier transform of this, it's actually very nicely structured. You can actually compute it exactly if you wanted to. It's basically some sines over x. And now let me superimpose these two images and translate this image. So what I'm doing is that I'm taking this image, I'm translating it actually by 100 pixels, and I'm adding some noise in the shape of this black square to the image. And if you actually look at the level set, it remains basically unchanged. So this is what I was saying, if you can even add some noise, and basically the Fourier transform where it spikes remains basically unchanged. You see it here, the spike is 14.8, here is 15.06. And now what are we interested in? We're actually interested in detecting the phase at this spike, okay? So, and this will actually give us an idea of how much the original image was translated, okay? So if I detect, let me now do something spurious, okay? Let me detect how much this image, let me pretend that this is a translation of this image, which it obviously is not. So I expect to get a nonsensical result, right? And indeed, if I run this previous algorithm on this image against this image, and I read off the phase that I obtained by looking at the phase of this spike against the phase of this spike, I'm going to get an absurd phase which has x 245 and y minus 198. Okay. So this is a completely absurd. Phase, and it's absurd because actually they're not related. Okay. But now these images are actually related. So let me compute the phase change of this spike versus this spike. And what I get is actually 100.00001 99.999998. So basically I'm detecting the scroll correctly, even though there was noise superimposed on it. Okay, so this hopefully convinces you in a more experimental way that this algorithm actually makes sense. Okay, and so scroll detection is actually quite useful when latency hits around 30-40 milliseconds. So this is actually quite useful if you're using this program over rather slow Wi-Fi, which I sometimes use. And but over a local network, it actually makes absolutely no difference. And in fact, p9wl with scroll detection is quite usable even when latency is 30 to 60 milliseconds. So I often use it even over the internet actually, not just local networks. So there's another bandwidth optimization that we actually do. So 9p is actually a sequential algorithm, right? So this means that each time that you write something, you have to read off the answer. And if you did things in this way, if you send a tile and then you had to check the answer, send a tile, had to check the answer, you would have a huge latency bottleneck. So instead what we do is that when we, for example, when we're writing to the screen, we send all the tiles at once without actually reading the messages that come back. And another thread actually reads all the messages, the acknowledgement messages as they come in. And this works fine, except that some parts actually truly need to be sequential. So when we reach these parts, for example, when a window needs to be resized, we basically need, this drain thread needs to receive all the responses back, and then we have a sequential part, and then we can, once we're done with the sequential part, we can go again into not caring so much about the responses. Okay? And okay, so finally we also need to handle the keyboard, mouse, and snarf devices. So this is not particularly interesting. So when you, there's a separate thread that reads from the keyboard device. So when it reads something, it calls wlroots. So it's the same story for the mouse. If we read something from mouse, we notify. And it was also something that I learned that was kind of odd to me, but it's actually the mouse device that sends the signals about window resize, which to me seemed a bit like maybe the wrong place for this to be happening. Okay, and finally there's also support for the snarf device. So if there is a copy happening on Wayland, we immediately get a notification, so we just write into the snarf device. But from the 9th front side, there is no way to know, so we actually need to poll 9th front every 500 milliseconds. Did the snarf content actually change? Okay, and if it changed, we feed it back into Wayland. Okay, so there are some things that I wanted to make work, but which I couldn't make work. So if you're using fractional scaling and your fractional scaling is not an integer, then scroll detection is useless. So it works, we correctly detect the scrolls, but we cannot make use of them. And we cannot make use of them because when you have fractional scaling, there is bilinear interpolation between the pixels, and when you take an image and a scroll image, all the pixels differ because of bilinear interpolation. So in the paper I discuss it in more details. It was a bit confusing actually why this is happening. And one attempt at getting around this that I had is to internally actually do fractional scaling by integer, which is just the ceiling of the fractional scaling that you intend. Then actually scroll detection works correctly, and also the scroll optimization works correctly. And then the idea was to send back those images with a scaling down command to 9th front, so that internally we are scaling up to an integer, and then when we are sending this back to 9th front, we send a command to scale it down. Okay, and so this was supposed to work, but unfortunately it hit a bottleneck, which is that this A command is actually a bit slow. It's quite CPU bound, and if you're issuing a lot of such commands, which is what is happening here, it actually creates a big load on the CPU, results in poor performance, and the whole optimization just doesn't make sense. Okay, so I want to finish with some minor experimental data. So here is the kind of, you see the full bandwidth for the terminal, and then this is what you would get if you just use damage tracking. Here is what you would get with scroll detection and with compression. Of course, you see that scroll detection makes no difference when you are watching a video, for example, and compression is what actually takes the entire row. But when you're scrolling, for example, in a browser, scroll detection actually makes quite a big difference. Not as much as compression, but if you couple it with compression, you're actually improving compression by a factor of 2. So you go from 6 megabytes to 0.4. And in fact, VNC would give you like 38 megabytes per second, and here you go to half a megabyte, so it's actually quite an improvement. And okay. And the latency is also good. So in the paper there are some graphs related to that, which I don't include here. And I think I'm running over time, so I wanted to thank you for your attention, and I wish you a very successful workshop, which I really hope to be able to attend it, but unfortunately I wasn't able to.
Okay, so first question is, do you have any numbers on how long it takes for just the CPU time, the CPU overhead of the Fourier transform and so on?
Oh yeah, okay. So I think on like really low kind of, low quality hardware, it can be kind of taxing. I don't have like actual benchmarks. I have some lower end computers, and the CPU load is maybe like 5% on H-top. It's not terrible, but it's noticeable. I mean, the Fourier transform computation. So it makes sense to also disable it. You can put like fractional scaling 1.001, and then there's no scrolling optimization. So the Fourier transform is actually not being computed. But I'm using this, Fast Fourier Transform library. So it's actually very highly optimized.
this was quite an interesting talk. Thank you very much. I'll
Thank you.
also jump on the FFT stuff a little bit. It looks like it rhymes quite a bit with the JPEG and what MPEG are kind of doing under the hood. How much? I mean, I don't know the internals very well, but how familiar are you with what those algorithms are doing, what heuristics they're using, and how far you want to carry yours into that territory?
So, I was actually not familiar with MPEG at all. So this kind of idea of using the Fourier transform was just obtained independently, I would say, because for a mathematician, it's really the first thing to think about. So it suggested so very naturally. Then when I looked through the literature, I found that video codecs do apparently really do this, and they do something more advanced that I don't actually know how much more advanced what they do is. I think probably quite a bit. And I think it would be kind of interesting to maybe, I mean, I was thinking about this, maybe the whole thing should be thought of as replaying a video, right? So maybe the ultimate compression is we're kind of recording what happens on Linux and we're replaying this on Plan 9. That could be maybe the best way to compress. To really do it like a video codec, but I haven't explored this very much.
This is Skip. Yeah, I had a similar question actually. So, it looks a lot like MPEG compression, and well, I guess there's small devices have MPEG encoders usually built into them. So I think or decoders, I should say. But encoders, that would be interesting to like explore whether you could actually use like hardware that's I believe even the GPU on Raspberry Pi. No, yeah. So
can handle. Okay.
Yeah, it would be interesting area to explore whether you could use that hardware.
So I never tried anything on hardware, like Raspberry Pi. My hardware was a notch better, so I don't know how it performs on RPI. Yeah, but then it's interesting actually to look at. Yeah.
Yeah, really interesting work, Paul Lalonde here. How did you choose your tile size?
Tile size. So I think it was just, experimentally. I mean, if it was 32 by 32, it felt a bit choppy, too much being transmitted. 8 by 8, too much CPU, so kind of 16. I mean, it was just kind of like experimentally 16 by 16. There was no real rhyme and reason there.
Okay. And your higher level tile, apart from you have a 256 by 256 size tile in there as well. Right. What's the significance of that particular size?
Well, that was also experimental because initially, I was just doing Fourier transform on the entire big screen. And then this was bad because when I was resizing the window, then the whole thing was actually becoming very slow. And then I realized it's more advantageous to keep 256 by 256 because I can also run them in separate threads. So I split, I run each Fourier transform on a different CPU thread. So this actually works faster thanks to this.
Cool. Yeah, that makes a lot of sense. Did you try anything on, detecting scrolling boundaries, trying to see if it's possible to use your Fourier approach to find a slice down, usually it's an edge of the screen or a bottom of the screen?
Yeah, no, I didn't try this. No. This I think, at some point I also had to keep it not too complicated.
Is where your intuition is on the diminishing returns for that?
I think, in a sense, scrolling is already, in a sense, a diminishing return because it's only noticeable when you, for example, when I'm at home, sometimes I connect over the internet back to my computer and I use this thing to use Linux applications, which are in my office. And then scrolling actually kind of makes sense. But if you use it, on a LAN, you just don't notice anything at all. So it's already, in a sense, scrolling is already a bit of an over-optimization, I think.
Very cool. I'm looking forward to trying it. Thank you.
Thank you.
actually, back here again. Ori, on the topic of scrolling detection, have you considered trying to use the damage regions as a heuristic for that?
Oh yeah, it is already using that because sorry. No, we are we using that? No, we are not. Okay, I'm just thinking if I actually do this.
Because my theory is that
yes.
if you're scrolling a region, that'll be the damage region every time.
Yes, it has to be always the damage region. Yes, I just don't remember if the code actually already narrows down only the scroll detection in the region that has damage detect. I mean, I don't remember if it's already doing scrolling detection only the damage region. So I don't remember, but it should, right? It will be better.
All right, looks like that's it for questions. Thank you.
Thank you.